We've heard about the risks in cyber-physical systems this morning and how we can assess and identify those risks. And then later today and tomorrow, we'll hear a bit more about resilience measures that we can put in place in our cyber-physical systems to keep them operating safely and stably when an attack does occur. But the step that's in between those, I suppose those two pieces would be the detection of attacks. So how do we alert the resilience systems when an attack does occur in our network? So what we've been working on as part of the Sparks project in Dell EMC and with the RSA security division of Dell EMC is this attack detection piece. Okay, so the first thing I want to do is introduce the system and the assumptions about the system that we're working on. So we look at the smart grid infrastructure for the energy grid, and we look at the consumers, both residential and business consumers, so large office buildings, like the Nimbus microgrid that Paul has mentioned earlier, and I'll talk a little bit more about now, and various different industrial control systems. And then we also have the utilities, so generating, storing, and distributing energy. And across this entire network of consumers and utilities, we have smart meters that are measuring data, and we have controllers that are sending commands and actuating depending on the data that's being measured across the system. So we're assuming that we have, for example, wireless connections. We have remote connections here, might be wireless, might be wired, but essentially they can be there are vulnerabilities there introduced by these smart meters. So if we look more specifically at the Nimbus microgrid, which is one of our test beds in the Sparks project, this is a building in Cork, in one of the university campuses in Cork, which is divided between, I suppose, an incubation centre for startups and a lab where they do a lot of experimentation. So we have power generation through a wind turbine. We have batteries to store power whenever there's more generation than consumption. There is an optional connection to the outside, the external mains supply. There's heating, a combined heat and power unit, and that controls the heating system throughout the building. And then we also have various lighting and lab loads. And this entire building is instrumented both from the electrical point of view, where we have a SCADA system that measures 8 different points throughout the building, 18 different electrical variables at each of those points. And also then the entire heating system, the water leaving the boiler, coming back, and all the different temperatures throughout the heating system are fully instrumented in the building management system. So if I can go the right direction this time. So that's the system that we're looking at. And then the next thing we look at is the attacker and who we assume that the attacker is and what they're trying to achieve. So we assume that the attacker's objectives are to disrupt services, to cause damage to equipment, and in some way to cause increased costs to the target of their attack. This might be through increasing the power consumption, or obviously the costs associated with equipment damage or services. And we saw a lot of that in the risk management, the risk assessment piece earlier. And in general, I suppose we assume that the attacker, that their goal is to maximize the impact that they'll have on the system. And that might be through carrying out a very abrupt and large attack that's short-lived but has a huge impact, or it might be through carrying out a more subtle attack over a long period of time, and by that increasing costs for their victim. So if we just very briefly look at, I suppose, a simplified version of how the attacker is going about entering the system, we'll assume that they'll gain entry to the system, they'll carry out surveillance to extract information and learn about how the system is working, and then they'll intercept some of the variables and commands that are being sent throughout the network. And then ultimately, we're assuming that the attacker is going to manipulate these variables and commands in some way. So Just to put into context the security analytics work that we've been doing, you'll hear a little bit later from Bujang, who's one of my other colleagues in the Sparks project, about network intrusion detection and various other topics throughout this session. And I suppose we see these as complementary systems to each other. So the network intrusion detection is taking care of a lot of the initial line of defense, whereas we're looking at assuming that an attacker has got past that and now they're starting to manipulate the data, and we want to detect that happening in the system. So just to be more specific, we're assuming we're talking about man-in-the-middle attacks, and they're intercepting either of these directions of communication, either the variables being sent or the commands being sent back. And basically, when they manipulate these data, there are anomalies in the system. So there's behavior in our system that's not normal for the conditions. So the solution that we've developed is looking at the data itself. And we look at this in two different ways. So where network intrusion detection systems will look at the traffic and a lot of the different, the different method signatures and that in the packets being communicated throughout the network, what we're looking at are the actual values of the data that are being measured and are being received at the controllers and the commands that are being sent back. So we take two different approaches. One is to look at the knowledge we have. So if we take the Nimbus microgrid, I mentioned earlier that there are 8 different points where we're measuring electrical variables throughout that system. And at each of those points, we're measuring 18 different variables. And those variables have very specific, defined physical laws that relate them to each other. So for example, a very simple one is to say if we measure power, we measure voltage, and we measure current, then we know that the value we're measuring for the power should be the product of what we're measuring for voltage and current. And that's the simplest of various different rules that we've put together with our colleagues at UTRC in Cork, who are connected with the Nimbus building in CIT. And so we can look at these rules and we can look at the statistics. So there'll be things like measurement noise in the system, and we can look at the statistics of how these relationships, how the equalities are seen in the data under normal circumstances. And if an attacker manipulates only a subset of the variables that are being measured in the system, some or all of these relationships will no longer be satisfied. Okay, so we can use knowledge of the redundancies, knowledge of the topology of the system and the configuration, and we can use that to detect anomalies in the system and to detect data that doesn't satisfy the relationships it should. But that only gets us so far. So there are a couple of scenarios that this won't protect us against. Number one is an attacker who has gained enough knowledge to attack enough of these variables and to carry out what we call a stealthy attack or a zero stealthy attack, where the manipulated data does satisfy all of these physical relationships. It's physically valid data, but it's just maybe wrong for the time of day or the time of year or the other environmental conditions we have in the system. And the other thing is to look at, so if we again go back to the Nimbus system, where we have much more complex relationships. So the electrical system is very, very well defined and easy to define formal rules for. But if we look at the heating system, where we know that the temperature of the water leaving the boiler and the temperature of the water coming back is related in some way to the temperatures at the radiators in each building, in each room rather, around the building, to the external temperature, to whether or not the windows are open, the occupancy number of people in the room. There's a very, very complex system there, and it's unfeasible, if not impossible, to come up with formal definitions that are actually useful for the behavior and all the different dynamics in a system like that. And so what we do in those cases is we have a second form of anomaly detection that we use in our security analytics tool, and that's data-driven anomaly detection. So here what we're doing is we're taking historical data from the system, we're adding in extra environmental variables like the time of day, time of year, the weather conditions, and we're fusing various different sources of information with the SCADA and the building management system, and we're using machine learning algorithms to learn models of what normal looks like. And there'll be more than just one model of normal behavior, because, like I said, it will depend on the different conditions and the different context. And by combining the knowledge-based and the data-driven anomaly detection algorithms, we then come up with a system. Apologies. We then come up with a system that's more robust. So we can now detect the various different types of anomalies. So just to go a little bit more specifically, we look at the variables themselves. We have thresholds. So for example, we know in Ireland the frequency of the mains distribution is 50 hertz. So we can look and see, you know, that there are certain variables that just have thresholds themselves, and they have ranges they're allowed be in. There are the relationships, as I said. And again, we define statistical thresholds within which these relationships and the physical laws I mentioned earlier are deemed to be satisfied. And then what we do with the data-driven side is we take the raw data itself, we generate features, so they can be time domain and frequency domain type of features. We look at things like correlations between different variables, and we use all these features then to feed in along with the relationships themselves. So we take our knowledge that we have and we feed that into the data-driven models also. And what we do in this case is we use a single class support vector machine as our classifier, and that will then tell us whether we have anomalies. And then we can combine the different methods and we get the anomalies at the end. So we've built a simple user interface just for demonstration purposes. And for example, just this example here shows some of the data from the Nimbus system. There's not an attack as such going on here, but there's some unusual behavior in the system because of experimentation going on in the labs. And what we can see is at this point, both the rule-based and the machine learning-based anomaly detectors are both detecting the anomaly, whereas in another case, it's only the machine learning is detecting an anomaly because it's behavior that might be, like I said, physically valid, but not normal for the conditions. So finally, I just want to finish on some simulations of the performance. So the performance of anomaly detectors is, it's difficult to measure and validate, and this was touched on earlier when we talked about validating the risk assessment. And I think it was Martin or one of the speakers mentioned it's hard to know for sure that you've caught everything, okay? So something might slip through. Usually with classification algorithms, we look at things like number of correct detections and number of false alarms and your probabilities of those. Whereas what we look at here is if we come back earlier to the goal of our attacker to cause the maximum impact, we look here at the maximum deviation that the attacker can successfully cause in the system before they get detected. And then we look at that versus the expected time to a false alarm. Because false alarms in themselves are also costly, because if you switch into resilient mode, there are usually cost impacts in that, and also the investigation of what caused the alarm. So what we look at here are those two metrics. The simulation, I should mention, was done because obviously the Nimbus building is a live system, so we can't obviously carry out attacks on that. So with our colleagues in KTH and in UTRC, we have simulated attacks on data sets with a simulated model of the system. And basically what we can see here, the blue line is the knowledge-based detector, and then these three other lines are all the data-driven detectors with different sets of features. And what we can see is that for the same expected time to false alarm, we get a lower impact on the system with the anomaly detection, the data-driven anomaly detection in general. So that's everything I had. If there are any questions, I guess we'll keep them till the questions and answers at the end.